share screen. Okay, and so here the same teaching.complexword.net. There is the page. There is the recording of yesterday, the material of the course, and then I shall add the other two. So just for the new entries, a quick review of netlogo. So first of all, when you install netlogo, you have at least three programs. One is netlogo two-dimensional that we shall use. The other is the three-dimensional netlogo, in which you just okay. So in this case, you have a three-dimensional world, and so if you need, you can do things. For instance, let me show you, for instance, the Lorentz attractor in 3D. Lorentz. Should be this one. Okay, so for instance, this is I think you know, not the famous Lorentz attractor. Is not the differential equations that Lorentz developed as an approximation of the convective cells in the atmosphere. And this is the attractor, so you can rotate and you can say, check. For instance, here what I can do is, for instance, at a certain point, I can duplicate now we have not too many. Let me start again. So let me go for a certain amount of time. Then I clear everything. I reproduce. So now I have 81 copies, starting almost in the same position. And then when they go, at first they stay all together. Then, since the Lyapunov exponent, so the dynamics is chaotic, they start to spread. And at a certain point, this is the difference, the distance. At a certain point, they start to spread all over the attractor. And so this is essentially an illustration of their ergodic hypothesis. I mean that averaging over a single trajectory in a chaotic system is the same as averaging over many replicas no? at a given time. So essentially, if I take the of this, clearly in the limit of infinite number of replicas, is the same as following just one trajectory and computing time average quantities, no? So, and this is one of the basis of, say, statistical mechanics and so on. So this is, if you need to do something in 3D, you can also use this platform. The problem clearly in 3D is that it is not so easy to see what is going inside. So, no? Okay. So, but let me come back to the original platform. So for the new entries, this is a self-contained platform in which you have the interface here that you can design at your will. So you can put slide in order to change some variable, no? Some button in order to execute the code. And in the code part, we have the code. So for instance, setup, when I click setup, I call procedure setup. And so maybe clearly I'm going quick because we already have seen this in the last lesson, but there is the recording in case you want. So now, for instance, let's try to implement this. Let me see. There is a nice paper by Holm Neumann with this one. Essentially, this is one model of say opinion formation. In these sociological models, essentially one typically assume that if you are surrounded by, I don't know, many people that have a given opinion, then you tend to follow this opinion. And this is one of the classical models. It is essentially like a magnetic model, no? You tend to align with the majority of your neighbors. Another kind of model is that in which you don't change opinion, but you establish a relationship with those that have similar opinions. And so essentially these are models of clustering. For instance, these are techniques used also by, I don't know, Facebook and so on, in order to find the communities and so on. And in this model, they propose to do something in a mixture of two. So essentially, they have people with a given opinion out of a certain number of opinions. Say, a given color out of, say, I don't know, 20 colors. And each has there are a certain number of links among them, and the dynamics is given by a single probability phi, and says with probability phi we choose at random one edge of those attached to you, and you move it to another node that has the same opinion of you. So you tend to establish connections among people that share the same opinion. Otherwise, you pick one of your connected neighbors and you change your opinion with that of your connected neighbor. So clearly, if phi of phi is equal to 0 to 1, say, let's start with 1, you clearly only make, you don't never change opinion. You only make clusters of people that have the same opinion. On the other hand, if there are enough links that the whole network is connected, and you start changing opinion with those that of one of your neighbors, this is the voter model, and essentially tends with all people with the same opinion. So, no, clear, no? In the first, you never have an opinion disappear, and at the end, you have only disconnected clusters with all people, with each cluster formed by people of the same opinion. On the other hand, if the whole lattice is connected, so if there are enough links, clearly, if there are very few links, you have disconnected things, disconnected the islands, so nothing changes. But if you have enough links, then at the end, you should have the same opinion. So the idea is that in somewhere in the middle, you have some, say, critical value in which you have a power law distribution of size of networks. This is what is mostly observed in experimental data. That, for instance, if you take data from Facebook, you group them according to, certain, or YouTube, people voting for some movie and so on, you find that there are not few movies with many votes, and a large queue of movies with a few votes. So they are generally distributed in a very flat way, not like in a standard random process in which you have generally distribution like a Gaussian or a Poissonian with a given frequency. But we are not arriving to this because he is making simulations with a lot of numbers. But the idea is let's try to visualize these dynamics with a model. So I choose this because it is essentially only turtles, and I can show you. First I show you what is going to happen, and then we try to reproduce it. So this is the. Is it starting? Okay, discard. Okay, so the idea is that here I fix the number of people. So say 100 or 200 people. No? I distribute a certain number of links for each of them in medium, and with a given number of states. So for instance, is it working or not? Expect the command where this worked just probably I started doing something more. Okay, so you have let's start with a fewer number of people, say 50. Okay, so these are my people, just distributed at random, with random colors and random connections. And this is the probability. So if phi equal to 0, everybody has the same opinion at a certain point. If p is large, say near 1, essentially they separate in groups of a certain size. Okay, according to how many people and how many colors we have. In the middle, there is some more complex dynamics. We have to find in which there are, you see, larger clusters, no? With so essentially, if you plot the distribution of clusters, here should have the we should have the histogram if something is not working. Okay, but we can work on this. There are so for some value you have larger or smaller distribution, but this is just for practicing, not with the cellular automaton of the field, but only with the turtles. Okay, so this is the idea. As you can see, the code is as always not too large. Okay, so we want to try to reconstruct this now in order to practice also with links. Okay, so let's start from scratch. Clearly, then I shall upload this. So if you want, I can just upload this, but I would like to upload the steps also. If you have your own graph, it can be done. I don't know if there are, because there are also extensions, for instance, for dealing with matrices and so on. I don't know if there is an extension for building a graph, but we can work on this. There are also a large community of users, so they help you if you say, I have this problem. Generally, they help a lot. Okay, so let's start from scratch. Okay, let's start that we want to have, say, a slider in which we say n number of people or of people up to, I don't know, 200. So with this we shall, so here you slider, you add the slider, you say, okay, this will fix the number of people that I create in my word. So I put a button here, setup, and then we can code the setup. So to setup, and then so this is the idea for the new entries. When you press a button, you are invoking normally the process. You are invoking this piece of code, and this piece of code calls for the setup procedure. Okay, so since we are working with the turtles, we start with the create turtles, which creates a certain number of turtles. How many people? And then we can give to each of them some code, some command to initialize everything. For instance, set shape. Let me see. We could use, instead of circles, we could use this person shape, no? For instance, so set shape person, then set size, we can start with 1. And then we have to choose, say, a color or an opinion. So maybe we can just add another slider here, number opinion. I don't know, up to, say, 40 or 20 or something. Okay. And so now, for instance, we can set, let's suppose that, let's define the turtle's own opinion. I define now, because since I don't want to just work with colors, because it is much better to have just one number, and then maybe colors can be used. So set opinion one random number opinions. Maybe this can be plural. Number opinions. Okay. And then I can define a procedure for coloring the people that I shall define now. Okay. Okay. So let us define. Clearly, we have a lot of colors, but since most of them are just shades of the same color, there are a variable which is called the base colors, which are, say, red, green, blue, and so and so. We may add the white. This is a list. So we may add to this white and black, which are not here. Now you see that the white is essentially 10, and the black is 0, and they are not here, no? So maybe we can say globals colors. I add to base colors, so set colors, base colors. So I copy simply the list of base colors into colors. Then I can add 0 and 10. This can be done in 2 or 3 different ways. So let me try to first one is to add either to the end or to the beginning. So yeah, I can say set colors L put Colors. Yes, set colors. Set colors. L put white colors. So L put, just remember, you have to, at the beginning especially, you have to often check the syntax. So L put adds a value to the end of a list. It is a left put or last put. Then there is also F put to put it at the beginning. So one way is this one. Set colors, L put black. No? As if now I can ask show colors and set up recolor. Let me, for the moment, comment this recolor. You see that now we have added a 10 or a 9.9 and 0 to this list. It is clear how it works. Color, base colors is this list here. If I L put white colors gives back a list with the value put at the end. In general, in this language, like many languages, also Python, I think, you never alter something. You cannot alter a list, or you cannot alter something. You can just do something and maybe replace it with a new instance. It is not like C, in which you can change something inside the list. It is uncommon because this has a nice behavior for the garbage collector of the program or something. If I do it. Also, I think also MATLAB is done like this. So objects are immutable; they can just be replaced by others. Okay, this is one possibility. Another possibility is this one. If you make a list like, say, black, white, and the base colors. Let me show base. Why is not? Okay, it is not like this. It is list. Okay, you see that you can make a list composed by, for instance, numbers and other lists. So this is with the operator list. While there is another operator, which is a sentence, which flattens everything. So you can give several lists. For instance, a sentence, I don't know, 1, 2, and 3, and 4, and 5, 6. And this listed at the first level. So 5, 6 remains as a list because of the second level, but it flattens everything at the first level. So another possibility is to say set colors, sentence, I don't know, base colors, white, black. Just to say that and this should be show colors, they should be exactly the same. Just to say that you have to read a bit on the on the dictionary, because there are several ways of doing the same things. Okay. Okay. So maybe I can comment this so that. Okay. Now we can define this recolor to recolor. Remember, recolor now is a procedure that is called by a turtle. Essentially, in this language, you have yourself, which you are the observer. Then there are patches, then there are turtles and links. Each of them can send and receive message to the others. So to the color, simply set the color, set the color of the turtle who is receiving this, who is executing this procedure. Say, let me define also n colors. So say set n colors, length of colors, so that now I set the color, the opinion, module, and the colors. So now the first is turquoise, cyan, green, red, black, and then we start again. So set color, which one? Item, opinion, mod, and colors. So item takes an item of a list. The item is computed taking the opinion number, modulus the number of colors. So let's see if no, number of colors. Opinion. No, each turtle has a given opinion, which is a random number from 0 to number of opinions. Then in order to associate a color, say, recycling some colors, maybe this could be an option. So let's see. We have also to scatter the people on the lattice, otherwise we don't see anything. They are created all in the middle. So say set xy random x core, random y core. Just to scatter people all around, no? Okay. This is something more, no? Clearly, we have to, as always, start with the clear all so that we can. Okay, now we have something which is more or less what I had in mind. We have a certain number, 50 people scattered around the world, and with each of them has a given opinion. So if I inspect one of them, I say that he has opinion 23, for instance. This one has opinion 23. And okay, this is slider links per turtle. Say we limit it to 10. This is how many links I should establish, no? So that each turtle has 3 links in average. Clearly, remember that the links counts twice because it connects 2 turtles. So, okay, it is a link from turtle to turtle, no? It can be directed or undirected. Okay. So now we can say create. There is a create link procedure, which is a links, which is exactly the same as create a turtle. Yes, it's possible to. It is like essentially like a turtle. You can also edit. It is quite limited, but you can edit the shape of a link, so they can be curved or with 1 line, 2 lines, 3 lines, and so on. They can have labels. The problem with the create links, and now I'm thinking that I would like to avoid to have double links between two turtles, no? So maybe it is better not to create just links, but to ask Turtle to create a link with another Turtle which is not already connected. So let do so repeat a certain number. How many? Links per turtle times people, and probably we have to divide by 2 in order to have the right number of links per turtle, because each time I add the link, I had 2 links per turtle. No, so I think then we check if it is working or not. So ask one of turtles links per turtle. Questo is here? No, but if you want, you can put a parenthesis, but it should be like this. Then we check. So the idea is that now I ask one of turtle to establish a link with another turtle which is not already connected. Okay? So, and this is also for introducing you new operators. So the idea, so each turtle can create link with. So create a link with creates an undirected link, and creates a link to creates a directed link. So again, these are here. Create link. There is a link. There is, you see, several. There are create a link to. This creates a directed link from one turtle to another turtle. Create links to creates a link from one turtle to a set of other turtles altogether. Then from, clearly it is the reverse, and with is undirected links. So, okay, with who? One of, because you need, now we have to create, I put parentheses, they're not needed, but just to understand. Now we have to create the set of all other turtles who are not already connected. So there is, so turtles is the set of all turtles. Other turtles is the set of all turtles minus the one who is executing this. Then there is an operator who are not, which is an operator that subtract from one set all that. And since there is also another preset set which is link neighbors, we have already seen neighbors, no? Neighbors are the patches which are nearby to other patches, while link neighbors are the turtles which are connected to the given turtle. So who are not makes the subtraction of this set from this set. And so in this way, if I have not made errors, so I put parentheses, but they're not needed. And then when we create a link with, we can also define, if we want, something of the link. For instance, if the link has to be a label, it is like a create a turtle. You can just say, okay, the link has to be green, doubles, so, or a certain style, and so on. but I think that for the moment this is enough. So we don't write anything. Let me see if there is some error, not so evident. Okay. So you see that, let me see, that put create 0, no links, okay. 1, we have a certain number of links, and now we can check how many links we have. So we can say report count links divided by count turtles. This should be the number of links per turtle. Maybe 2 times count links. And okay, you see that actually this is quite good. If we put 2, okay. And maybe we can also check by hand. If we put, I don't know, 6 people with 3 links per people, this has 1, 2, 3, 4. This has 2, so the average is 3. This has 3. This has 1, 2, 3, 4, 5. But this has 2 and this has 2, so the average is exactly 3. Clearly, we may prefer not to have periodic boundaries, so that you see all links stay here instead of wrapping around the world. Here, up to now? Okay, so this is, and now we can also exploit another nice thing, which is layout. There are several ways of distributing turtles in a given layout. So, for instance, there is a layout circle. Say, for instance, layout turtles in a radius of, I don't know, 5. Layout circle. Okay, so it arranges, maybe we can add some more people. It arranges things in a circle. What it is interesting is this layout spring, which essentially behaves, so makes each link behave like a spring of a given length, a given strength, and tries to arrange people with this. Since I don't I have copied this from another script. Let me open another. Let me copy it, because I don't mind me later. But I have to open another copy by hand, because otherwise it tries to open to close this one. I want to open another copy of netlogo, but it doesn't allow me to open, so I have to open by hand in this way. I think in Windows is the same. In Linux it should be much easier to open more copies. No, in general you can. This also is Unix, but the interface tries to open just one copy, because maybe probably people thought that this was simple to do this. So okay. Okay. The idea is we can just copy this. with the numbers that works. And I think I have to repeat. So let me copy this. I can make it to arrange. Let me copy this. Now I shall illustrate. Okay. So this clearly, this simply repeats 10 times what is going on. This says, okay, take all turtles that has some link, essentially. No, turtles with any link neighbors, or should be also any link here, but and they say, okay, the links should behave as a spring with a given constant, I think 6, a given rest length, and I don't remember what is this one. Let me see in the dictionary. Layout spring, say a given turtle set, a given link set, because also links can have different types, you know? So you may have, I don't know, parental connections and the friends connection, and you want only friends connection behaves in this way. You see, spring constant, spring length, and repulsion constant. Okay. So it is a spring that have a certain constant when it is below the natural spring length, and a certain attractive constant when it is above, when the distance is above this level. I think that this works. So let me see. I can close now this one. Say, maybe I can arrange. Let me see if it is works. So set up. Maybe we can add more people. I don't see much this arrange, but we shall use it in the following when we change. Okay. Now I can also save this on our shared directory. So say Holm Newman. Here, netlogo Perpignan here. Okay, and since I'm citing the paper, I may add the reference to the paper in the info, so I can show you also the info tab here. So let me take the paper, this one. So here you can edit, say is what is it? An implementation of the algorithm of say this non-equilibrium phase transition. Peter Holmes and Newman, physical review letters something. I can put also the DOI. Okay. Just to how to document things, no? Okay, I can save. So if you are interested, you can retrieve this. I think you can also put links, but okay. Now, in order to continue, we now have to implement the real algorithm. So this is not used anymore. So we add another slider, which is our fee. From 0 to 1 step, I don't know, 0.01. This is the control parameter, no? The one that, okay. And a go button. Okay, so now this is for setting all things. No? Then we press setup, then we decide how much should be this file, and we proceed. So let me try to go, and to go we have to let's take again the Holmes. Maybe I have closed it. Where is it? Here. Window Holmes Newman, this one. So he says, okay, here. With probability phi, we select a random one of the edges attached to a given turtle, and move the other end of that edge to a vertex chosen randomly from that of all vertices having opinion G. So let's try to implement this. So for the moment, I don't put the if phi. I just do this. No. So ask one of turtles, but it could be one turtle without any link. So with any neighbor links, no? Link neighbors. I think we could also have used another. I don't remember. There should be also an operator that says this says, okay, all turtles which have a neighbor attached to a link. But I think that we could also have just links, but I don't remember. Link related, or turtle related, let's say. Turtles. No, this is built-in variables. Turtle related, link. Create a link with, create direct the link in from is direct is link is this is link related. Okay. Let's say that it is good. It is working, so I don't want to investigate too much. Okay, so I ask with any turtles. So I now need to say destroy one of the links. If let me check the dictionary, should be there should be a links here. Links. This is the all links. No, my links should be something like my links. Links on. No, this is it is like turtle's own. Is to define variables attached to links. Should be my links. My links. My links. There should be my links. My links is the set of all links attached to a given. No. So here we could also use any my links. No, it's the same. Okay. So ask one of my links die. So I destroy one of my links. E poi create link with something like this. One of other turtles who are not link neighbors, and with let me just define a temporary variable. Let my opinion I shall show you that we can also avoid this, but with opinion equal my opinion. So first I would like to show this, no? So I take one of links and I drop it. Then I save my opinion in this temporary variable, and then I want to create a link with one of other turtles who are not my link neighbors and have the same opinion of myself. Maybe I have to, let me say, if any this, yeah, because if there are no other turtles with the opinion of myself, this returns an error. No, I cannot do this. So in order to avoid this, so if you want, we can just say let my set this or my target. Just if any my target, one of my target, just to say, to make things more simple to read. Okay, just not to otherwise I have to repeat this long phrase again. And so now here I have used this variable. I could also, let me copy this, I could have also said opinion of myself, but clearly it is so opinion myself is who is calling, no? So opinion of myself is my opinion. I generally prefer to define a temporary variable, but you could also write it this way. So opinion of myself is the opinion of who is calling. Okay, now the problem is that when you take with, these things that is written here is executed by the turtle who is receiving the message. So I'm sending a message to all turtles that have survived this selection. No? And then I ask all turtle, who has an opinion equal to my opinion? And I aggregate this set. So now this language is using sets. So you take the set of all turtles. Then you take from these turtles, you leave all that, so you keep all that are not link neighbors. You remove myself because it is other. And you select from this those that answers true to these things. But since this is a message sent to the others, I have to specify this is their opinion. Okay, so I have to say it is like asking to all of you, who of you has the opinion of myself? Has the same opinion as myself, no? So either you define a temporary variable like this, which I prefer, or you have to write these things here. But I'll put here commented. Okay, so if any my target, create a link with one of my target, and this should, now we check, and then we proceed with the other. So let's see if this is working with a limited number of people. And expected and not with, and let me check on the other. to go, let my state, if else random, if any my links, ask one of my links die, let targets other turtle with state, I have to put with before, not end, but other turtles with this who are not link neighbors, not okay. With because with had to take an agent set and apply something and filtering the agent set. So I cannot put there because it took link neighbors, which is not the right agent set. No, because if I put this here, okay, this with, first of all, I put an end here, which is not good because with wants to have an agent set on the left. But if I don't put this, this selection operates on link neighbors and not on turtles. Because if I put it like this, it takes link neighbors. With the opinion, exactly my opinion, and they remove this set from other turtles. No? While I want to have all turtles that have my opinion, but not who are not my neighbors. No? So just to documentation, let me, okay. So, sorry, but it is not so easy to write down everything, thinking to what to do. Let me see. Create link with one of my target. Is singular. Okay. It seems that at least there is no formal error. Let me see. So setup have this. Ask, say, watch. So that I should be able to watch myself. Let me see if this works. No. Watch is observer only. Okay. I don't watch it. So go, okay. I have removed the one link and maybe I would like to watch the, let me see. Let X1, this one. Copy. Just to select, no? Watch X, so that, okay, so that we can see who is going to, and then ask X. Okay, so, okay, now you see that at least we can have the idea of who is going to perform the action. Now we may say wait, I don't know, 1 second. Okay, setup. So let's say I watch this and removes one links, and but I haven't seen probably let go another. So it removes. I don't see the establishing of new links. If any, my target. Okay. So we have to modify a bit because we have to be sure that we have a target before. Because otherwise we just destroy links. Okay, so watch X. Wait one, okay. Let me ask, say, let my target, something, 0, just to define the variable target. No, okay. not this. Ask X. Let my opinion, let my target, let just move this before, no? If any my target, then I can drop a link and create a link with one of my target. We have to do this. Okay. We can say, let's say with elf user message cannot change link, just to show another thing. Let me see if it works. Go. Okay, this works. Go. Cannot change link. Cannot change link because we have too many opinions for the number of people. So if I reduce the number of opinions, should be easier to, you see? Okay, so this is nicer to see. So then we can say, make this forever, and you can see the, okay, here cannot change link, and you can see the algorithm working. Okay, so maybe we can remove this user message, or okay, but since we have checked that this is working. Okay, then we can implement the other. So let's say if random, if else, random float 1 less than phi. I don't remember which one was with probability phi and which one was probability. This is with probability phi, and the other is with probability 1 minus phi, no? So watch it. If else random float less than p, we do all this. Else we change opinion. Set opinion of one of link neighbors, and recolor, because since we have changed the opinion. Clear? So now I have inserted the possibility of doing one of the other things. Then and see, after this I may ask arrange, because I have changed the links before, so I may rearrange things so that they look nice and not they clustered together. So let's see. You can opinion in observer content. Why? Okay. I have to ask X. Ask X. Set opinion. Okay. Probably I could move ask X outside the cell if else also, but okay. No, arrange is a procedure for the observer, not for the turtles. So set up, go. Take this, take this. Now phi is small, so okay. Now if I put the phi large enough, I see things rearranging, while if P is small, it is simply changement of opinion. Hmm? So in this way, you can see how the things evolve. Clearly, then we have to say speed up things, so we can remove this weight and probably also the watch. Or maybe let's do another thing. We add the switch here, say watching, okay, and so we can say if watching watch X weight 1. Hmm? So if watching is off, we go all speed. Otherwise, we have time to examine what is going on. Hmm? Okay, so this is a completely different example of what we can do. Yes, yes. Clearly, for instance, we can. So maybe I can show you now some example of how we use this. For instance, one. But first of all, let me see if everybody has arrived to this point. If you have questions on this code, if you want to propose something new, I don't know. Let me. So, for instance, we could change the shape of, you see, you can edit the shape of the link, so you can add, I don't know, different kind of lines. No? I haven't understood, sorry. Predefined models in where? To do what? Come-ins? I don't know it. Okay.
The answer is yes, because I've checked all the
No, clear.
all some of the library, and there is a library already implemented, which is called here. There is one called Camins. I think it's in mathematics. Oh, okay. There's a way to
Come,
Camins with the K of kangaroo.
okay. Come like this.
K means
Okay.
KM.
Huh. Come, Kami. Write it. Kai means. Okay. But it is like this. Clearly. Yeah, so I have never seen this, but clearly you have all code here. So
Yeah, let's say that you have a group of points. and we want to separate.
Okay, yes, a clustering algorithm. Okay. Ah, yes. Now I understand.
Two wings. Want to separate here. It's quarantine 6.
Yes.
This is 6 mean.
I think this is the number of centroids.
The number of cluster is the tau of Camille.
Yes.
So if you want up.
This is number of clusters.
If you want
So 4 clusters, but I think this is for generating, and this is for interpreting. I think. So I think that he generates a number of clusters, and then you have to interpret this with another number of clusters. I think. Find clusters. So. To push, you mean if you can upload your graph? Yeah. Yeah. Yes, clearly there are other tools for making analysis. This is for, say, showing things. Yes, but for instance, I remember another clustering algorithm, which is the super paramagnetic clustering, in which you essentially each point acts like a magnet, and it aligns with a certain probability with neighboring ones. Okay, so and so just to show you another, for instance, this is a paper. So I use this. Let me see. One of these. I don't remember which one. Probably this is. So essentially, this was to illustrate a model that we developed in order to simulate the accumulation of knowledge, for instance, in Wikipedia. The idea, or in reality, it was in a search for in archive for a number of papers. But the idea was that so we were studying how people say, okay, how humans accumulate knowledge, say in mathematics, where you have to perform. Yes, exactly. Why it is in all cases, not generally shapes like this. So you start making a lot of big discoveries, and then you slide, start filling holes and so on. So the idea was that you could produce a new piece of knowledge up to a certain, say, distance, giving that in the corpus there are already a certain number of prerequisites. So you have an intuition of a new theorem. If and the theorem says, okay, if this is true, then this is also true. But the prerequisites maybe sometimes are already in the corpus. Otherwise, it is a conjecture. No, you make a conjecture, say if no, this were true, so this is also were true. And so the idea is that, okay, let's suppose that you can add new nodes. If for each node at a given, so first of all, it has to not to be already present in the corpus. So you choose a dots, which is a location which is not already read. It should be at a maximum distance from the highest point of what you already have. Each of them has a certain number of dependencies chosen at random below it. If they're all present, then you add the new theorem to the corpus. And so, then clearly we can perform computations and so on. But the idea for illustrating this is essentially this one. No? So you see that most of times you don't do anything. At a certain point, maybe let's start again. At the beginning, it is quite easy to add new things. Then and at a certain point you still continue to say find the variations of already found new theorem. At a certain point there is an advancing, and you see that the number of holes, what is interesting is that I'm not trying to fill in the holes. Holes is a missing point below the maximum of the knowledge. So, okay, how it works. I choose one point at random from the top plus a certain distance to the bottom. If it is already occupied, nothing. It means that I have the intuition of a theorem which is already present. So if it is empty, I choose three other items below. If all of them are present, then I add the new theorem. So there is nothing that tries to fill up holes here. But essentially what you notice is that the number of holes remains constant. No? So instead of having a fractal-like growth, you have a rather compact growth of this knowledge. Even though you don't try to find, so to fill holes. Clearly, in the literature, it is often said that this slowing down is due to the fact that people concentrate in finding holes, finding theorems that are not so important but are easy to demonstrate, instead of concentrating on, say, a large breakthrough. This growth fits quite well with Wikipedia. So if you look at, so you clearly in Wikipedia you find the holes only when you see how links are populated. So you discover a hole because at a certain point there is a page that is edited adding a link to the new. Yeah. But okay, well, this is just for showing how you can use netlogo to illustrate some idea. No, you have noticed that explaining this is already difficult. If you have an animation, especially now in a conference, it is easier to say to illustrate the problem. Ah, yes, it's total production. Ah, yeah, yeah.
In terms of scientific solution,
Sure.
we are everybody.
Yeah, sure.
Same from researcher.
And so, yes, for instance, yesterday we worked on life, no? Now, for instance, so we had this life. Let's try to add a plot of, say, how, for instance, the number of living cells behaves in time. But first of all, we shall come back to this. I would like to show you another usage of netlogo that may be interesting for you. Just using netlogo for so here the word is hidden somewhere below this. Some place there should be a small word which is not really used. I don't know. We probably have to move separately each of them. But I don't know where it is. The word, but I don't use the word here. I just use the plots, for instance, in here to visualize the logistic maps, how now the trajectory. This is the logistic map. The logistic map is just this iteration, x is equal to ax times, do you know it or not? Okay, so let me introduce, so this is a model of population growth, no? Normally, this was developed in the 70s. Normally, when you think to, say, modeling a population growth in an environment which is right constant, you use a differential equation. So you say that the number of animals after, say, 1 day is the same as before, less those who died, plus those who reproduced. No? And the one way of modeling the limit of resources is to have reproduction that depends on the available free space. No? So x is essentially the number of animals with respect to the maximum number of animals. So it goes from 0 to 1. But when it is near to 1, it means that you have a little space to eat and to find a nest and so on. So the reproduction rate goes down. So if you interpret this as a differential equation, this is called the logistic differential equation, and it gives you a growth and then a saturation. And this is what has been used. So, no?
No, but this.
The logistic growth, yeah, but we don't use it for microalgae. It's kind.
Okay, but
we use exponential growth.
Yeah, this shows the differential equation shows exponential growth when x is very small, because you can throw away this, and so you have essentially exponential growth. After saturation, it starts to slow down and then saturates at a certain level. But in the 70s, there was this Robert May who was studying insects and say, okay, insects do not behave like this. Generally, they lay egg at the end of the season, and the new generation is not overlapping with the old one. So you cannot use a differential equation to model this, because it can vary widely from 1 year to the other. And so he said, okay, let's now suppose that the number of animals at the next time step, next year, is the same function as we have supposed for the logistic growth, but without overlapping. So it is not a differential equation, it is a difference equation. And so this ax times 1 minus x is this parabola. Let's eliminate this. So this is the x ix times 1 minus x. So it goes to 0 at x equals 0, 0 for x equal to 1, and has a maximum as and at half over 2. In 1/2, a over 2. Okay. And in order to iterate this, an easy way is that of, say, start from some point, find the value at the next time step, go to the diagonal, so practically report it on the x-axis, then go to the curve, then go to the diagonal, no? And so you find, for instance, here a fixed point. This is the time series of the population, no? So you see that if the reproduction rate is less than 1, goes to 0. So if you produce less than 1 offspring, clearly population goes to 0. If the growth is greater than 1, you have a bifurcation. So there is an unstable fixed point in 0, because clearly if you start from 0, you don't have any insect. And you have another fixed point, which is independent of the starting value. No, you see that the initial condition is here. Here you can say, you see, you have the dependence of the initial condition is here, then you go to the. Then, if you increase the reproduction rate, at a certain point, you have still fixed the point, but now the convergence is oscillating instead of being monotonous. Then, clearly still independent of the initial point. Then you have it that this point becomes unstable and the limit cycle appears. Now you see that now there is a limit cycle, I mean, oscillating between 2 points.
The condition of the system does not allow the population to converge to the stable point, the fixed point.
Fixed point is unstable now. You see that we start near to this one.
Because the growth rate A is the value of the growth
So
rate
this
does
is
not allow it to converge.
this equation can be found also in other fields like in chemistry. This is called the period doubling bifurcation. So instead of having just a fixed point, now you have a bifurcation. If you increase A, it arrives to a period 2 bifurcation, a period 2 trajectory, a period 4 trajectory, another period doubling. And then there is a cascade of period doubling until chaos. And then you can have periodic windows also inside chaos. For instance, here you have a period 3, no? Window inside chaos and then fully developed chaos, say with the. So you see that you can animate these kind of things. And if you want, so maybe I can also save this on the shared directory. And if you want to have another look, you can look at this. So here is A from 0 to 4. So essentially, for each value of A, I am performing a simulation, throwing away the first 5,000 iterations and plotting the other 1,000 points with a pointer. Okay, so you see here, A before 1, only fixed point at 0. Then it becomes unstable, and another fixed point appears. Then here you have the first period doubling. Then you have the second period doubling, and then there are others. Then chaos appear, these black things, and these are the periodic windows. What is interesting is that now I can enlarge this part. You have again the same scenario. So this is a kind of fractal. So if you can increase the resolution, and you always find something similar. Okay, so you can use also for doing this. Now, this is the word. I'm using this with, this is my word with wraps and so on. Okay, so it is essentially I'm using a turtle, which is invisible, to go there and drop points when.
Yeah, for one value of A, there is 1,000 points.
1,000 points, exactly. 1,000 points. So you can see that if I put very few points, you see here there are very few points, only 30 points. I can make only 10 points. If I reduce the transient, you see all the trajectory before reaching the fixed point, no? Okay. Because you start at random and then you have to reach this and if I don't eliminate the transit, you see all the transient here. So just to show that you can use this for say illustrating things, bifurcation diagrams and so on. Which is the Lyapunov exponent, but okay, not very important. Okay, I can save also this one. If you go in the web pages there are a lot of the other models. Okay, so I think we can just stop for a moment so that we can have some rest. And then we may discuss a bit of what you could develop if you want, try to develop by yourself.
Okay.
So let's say that we come back at 17 in
Okay.
quarter of hour. Clearly, if you have questions, please ask those who are at remote, because I don't see them. At 4, yes, at 4, 16. Yeah.
Alors, vous faites.
J'ai essayé au début, mais quand j'ai pas les comptes du début, j'ai.
Ah, il va vite. Bon.
J'ai compris le principe, mais franchement, je.
Voilà.
Mais
Pour réfléchir à comment toi tu peux
justement,
utiliser.
j'ai un peu réfléchi. Je sais qu'il y a plein de choses qui prennent. En gros, moi je travaille sur essayer de modéliser les événements de cascading dans le code vidéo.
Le monsieur, c'est pas ce qu'il sait.
Oui, mais justement, et ces événements cascading, c'est une audience qui se forme à la côte et qui est formée à partir de plusieurs paramètres atmosphériques. Et je me demandais si, en déterminant un point nécessaire pour chaque paramètre, je vais déclencher cette cascading, donc c'est tout qui va plonger dans le code vidéo. Est-ce que ce serait possible de modifier quelque chose comme ça, ou il faut que je mette un poids à chaque initial, à chaque paramètre, et ils vont évoluer, et ils vont, s'ils arrivent à un optimum ou à un seuil donné, ils vont réussir.
On peut essayer, il faut essayer de décrire les choses. Oui, on se dépose un moment et
Oui,
on commence à penser, oui. Je prends le code si la porte ferme, sinon on n'entre pas.
Une formation informatique. Maintenant, sciences de la Terre. Ok. Et je suis là, master de géosciences et géophysique du programme. En fait, un tiers du programme, c'est la programmation Python. Ok. Parce qu'on apprend à être efficace, alors tu programmes.
Ok. Vous êtes encore. Are you still here, Namdi and Lucille?
Yes.
So, do you have some proposal for a model or? No, if you don't have, I'm asking to all of you if you want to try to discuss some idea, some.
But I'm still thinking, but I think it might be useful to modelize like as interaction between particles inside the material.
Mm-hmm.
But I just don't know yet how to do it.
Okay, we can. Okay, let's. One proposal is try to model some physical interaction among, say, material and. Okay, another suggestion.
We have prepared. Okay, it may be a bit complex, but we are thinking about implement a population of individuals, which with the possibility for one individual to mutate for another phenotype and see, according to different conditions, if it can replace the initial population. So it is maybe a possibility.
Okay, so a model of evolutionary system. Okay.
Actually, I think it could be almost the same one. I think, like you said, modeling the evolution of the phenotype of one individual, and I think I could apply it to the molecules also. So I think we can like mix them both.
Yeah, maybe, yeah.
Sure.
I've done some Google Scholar bibliography, maybe, and we have some program of irrigation here, and I've seen there are some agent-based model in irrigation, maybe, and I would begin a thesis supervising in 1 year or 2 years about irrigation and here. So maybe it can be an option. Okay, if you have an idea.
Well, you can still think, and I don't want you to force. Okay, let me try to, because irrigation was one of also of the project of one of my students in Florence, my PhD student in Florence. Let me see if I'm able to find what they did. I don't remember if in which in which folder was it. introduction, netlogo, 2023. It should be something like 2024. Let's see, netlogo. The problem is that I have too many. Netlogo 2004. So, for instance, this is a model of irrigation that was actually something is not really working here. Let me see. So essentially, this was how to say the presence of wind, how the diffusion and the inclination of the source of water influenced the. Now this is a model of say something who is throwing particles of water under a wind. So if you put the wind equal to 0 here in the middle, clearly things goes regularly. And this is the plot of the water arriving into the field. So you can incline the source of water. And so, for instance, you can say study what happens if you incline the pump against the wind, or you take everything in your face, but this is a particle of water. So this is clearly in this. You can also change gravity if you want. And so, okay, clearly. This just reminds me, so this was one of things developed by students, which is, so essentially, it is just a way of illustrating how we could do. While, so maybe I can save also a copy of this if you are interested in here. And so let's try to think to your model. So first of all, Lucille, are you thinking to a two-dimensional model? So where say particle have say maybe sputtering. So I mean, I have particles with a given velocity. They impact on some surface. They can, I don't know, bounce off or penetrate or something. So this could be one idea, no?
Yep.
And so, for instance, okay, let's try to develop this. While in your case, are you thinking to a spatial system or to a general? Because clearly you can have a lot of phenotypes. Then there is some fitness function. Then you mutate and you select those that, and for instance, you can have a kind of say mutation meltdown, selection, wild type distribution, all kind of things.
I think maybe more general model without a spatial part, just a number of individuals and maybe with different characteristics. Define exactly a fitness function, and according to the value of the fitness function, or
yes, let me, for instance, let me see. This is then I come back to your particle problems. Let me just illustrate what I did. For instance, this is a very simple Daisy World model, spatial Daisy World model. I think I have also the netlogo version. So in the spatial this is the mean field. No, this is not the spatial. This is the mean field. The mean field. The mean field. Probably I don't have the. It was so slow that I wrote it in C. So, oh, maybe this one. Let me see. Okay, in this case you have, this is your world. You have two phenotypes, white daisy and black daisy. Then I think you can also mutate. You have also the possibility of mutation, so you can have a continuous. Then this is essentially, these are just for setup. This is the empty fraction of the world. So if I put 1, you don't have anything. If you put 0, you have only black and white daisy. This is the fraction of white with respect to black. So if you put 1, you have only white. If you put this, you only have black daisies.
Excuse me, I think you didn't start sharing your screen.
Sorry. Yes, true. Let me share screen. Otherwise, you don't see anything. This one, share.
Okay. Thank you.
Okay, so let's start again. This that I can save, I can also send to you. This. Okay, so this is an old model about how life can influence the climate of Earth. So this is the surface of Earth. There is a sun. You can decide how many black and white daisies are there. So this is the initial proportion of black and white daisy. And this is a fraction of world which is occupied by daisy. This is the albedo of a black daisy. The albedo is a fraction of radiation which is reflected. So essentially, the ground reflects half, so 0.5. The black reflects only 20%, and the white 75%. And so this is the diffusion of heat. So if you don't put D equal to 0, each patch has its own temperature, while if you increase D, the temperature can diffuse. And each of daisy can survive only around this optimal temperature with a certain variance. So a certain interval, 0.1, around this temperature. Then they have a certain modality. They can, if they're in the same, the right temperature interval, they can give birth to a neighboring cell. And they can also mutate, but for the moment they cannot mutate. And we can say, for a given sun, okay, let me don't vary the sun. So for a given sun intensity, you clearly, if sun is too low, they die. There is a small birth, say, for remaining seeds, otherwise you don't populate. When sun start to be hot, at a certain point, some black daisy occupy the world, because since the world is still cold, only black daisy can survive. Then if you increase the radiance of the sun, at a certain point, white daisy start colonize the sun, the earth. So clearly they arrive to a given maximum, and then at a certain point they die. Or maybe we cannot arrive to this, but we could extend this this to say. So if the sun is too hot at a certain point, they disappear. But if we start and very automatically say slowly the radiance of the sun, so now it is slightly increasing by itself, and so you can see all the evolution of this planet. And you see that according to some parameters, you have a zone in which the temperature of the planet stabilizes, even though the sun is changing its temperature. So you can study this this model, so in mean field or increasing all these parameters. So, and clearly then you can also add the mutation, and mutation means that now you can have daisies of different, say, let's start again, different, if I have implemented, I don't remember if they are.
You can switch the phenotypes.
Yes, they can change also the phenotypes, so there should appear also intermediate colors of daisies. But essentially, they don't. In this case, they don't. It doesn't change too much this behavior. You see now you have mutants here now of intermediate color. You see now you have some shape of white, but clearly it doesn't change too much unless we start with only one kind of daisy. So maybe we just with black daisy. Now mutants can say establish themselves because they do not have to compete with already white daisy. And so now you see the evolution of say several mutants. You see that now they're starting to select whiter and whiter daisies because the radiance of the sun is increasing.
It's a continuous trait.
It is a continuous state. It is a continuous state. Clearly, then you can have a bit-wise code, but this is an example of. You see that now, no, they are becoming whiter and whiter because selection essentially is selecting tools that keep temperature lower. And I think that if we reuse the diffusion, selection should be more effective, since now all of them have to become white. Otherwise, they not rely on white around that cool down temperature. Now, because when you have high diffusion, you can say have a white or a black, a relatively black daisy who can survive because around there are white daisies that cool down the system. But if diffusion is quite small, everybody has to say evolve by itself, otherwise. And so this is so you can study all these kind of aspects of the problem. Another interesting problem in evolution, for instance, is the spatial Axelrod model. The Axelrod, I don't remember if I have it. The Axelrod model is a model in which people have to play tit for tat. So the prisoner dilemma. But I don't want to give a lesson on this. So this is more or less some idea, and so maybe you can think a bit of how you could implement when we discuss. While for Lucille, let me in the model library there are some physics gas lab, if I remember. some way of, say, implementing a gas, but so this is for instance how, in order to visualize the trajectory of a typical particle inside the gas. No, so I may, one thing that we could do, for instance, is to have a gas with a given temperature on a box and say how, and then a barrier, a penetration barrier in material, and see how many particles can sputter inside the material. This could be a possibility. And so we can either use this code, but which is not so simple, if I remember well. Otherwise, we could use the, I don't know if you know the multi-particle collision dynamics, Capral-Malevanez, because clearly we can also set up a molecular dynamics simulation. I mean, compute the force of all particles from force Newton law, determine, but it is quite slow. While the Capral-Malevanez multi-particle should be this one, or this, or the other. Maybe this. It is a very simple way of, say, modelize a gas that conserves almost all the properties of a real gas. The idea is this one. You have particles separated. They travel without seeing anything for a given amount of time. Then, when they divide, you divide the whole system into boxes. For each box, you compute the velocity of the center of mass of the system. So suppose you have two particles entering with the same or almost the same velocity in one of these boxes. You compute the center of mass velocity of system, which is essentially in the same direction. You subtract this to the velocity of all particles. Now they form a system with sum equal to 0, both in x and y. You rotate all velocities of the same amount, random angle, and you sum again the velocity of the center of mass. So essentially you have a mixing of velocity, unless you rotate by 0, or 1 or pi, which is essentially the same. And conservation of number of particles, energy, and moment, and the momentum. You don't have the local conservation of angular momentum, but globally it is almost conserved. So, and this is extremely fast. So we can try to apply, this is quite easy to be implemented in netlogo, since we have patches which are already the box that we need to implement. So let me try to implement one of these, which, if I remember, I did some years ago. So it should be the multi-particle collision dynamics. Should be this one. Okay, it is essentially, this is you have a free fly step. Then you remove the velocity of center of mass from each particle. you rotate them, all of them of the same angle, and you sum again the velocity of the center of mass. That's all. And there are computations that says that you can define, you can obtain all things, that depends on essentially on this time tau and the angle of rotation. So, okay, this is a good starting point for modeling a gas. So let's try to model this. Okay, so let's start with setup, a slider for the number of particles. Okay, let's try with 1000 at certain point. And okay, for the moment, I think it is enough. So let me use a breed particles particle, so that we can speak of particle instead of turtles. Particles on Vx, Vy, the velocity. Maybe if you want, we can also add the mass, if you want to have different mass of particles. Then particles. Then to set up, create CA, create particles number of particles, and set the shape circle, set size for the moment 1, set xy random, x core random, y core, set vx say 2 times random float 1 minus 1. So this should be between 0, minus 1 and 1, no? And then we can multiply by some factor. For the moment, let me just put here. Okay. And I think this is enough. So maybe we can make them of the same, say, set mass 1, set color white, just to have all kind of particles. Okay, now let's go. And so to go, so the first is the streaming. So let me define tau, globals tau and theta. Maybe we can say set tau 0.1, set theta, I don't know, 90 degrees. And so the streaming phase is ask particles, set x core. Do you want fixed boundaries or periodic boundaries? Let's put periodic boundaries. So I think we have to also to use x and y, because I cannot move a particle beyond the boundaries. So instead of let me set x random x core, set x core x, set y random y core, set y core y. So this is a set x plus vx times tau. This is the free, no? Now I have to check boundaries. I suppose I do not. So if x greater than max px core plus 0.5, because max px core is the maximum coordinates of the patch. And so the maximum of x is plus 0.5. Let me define something like this, because otherwise it is, we have to, max x, max y, min x, min y. So we can change them, because now then we have to put the material at the bottom. So to set up, say set max x, max x core plus 0.5, set max y, max py core plus 0.5, and the mean for the moment is like this. So let me advance. Okay, these are boundary conditions. So if x greater than max x, set x, I have to take x minus max x. This is how it went, beyond. And I have to, so this is here, for instance. So this is x minus xx. I have to put it to max x minus this. To bounce back. So it is essentially 2 of max x minus x. And set vx times minus 1. So if x less than mean or less, let me say less or equal, but I don't want today, mean x. So now here is x. This is mean minus x is the amount, and I have to sum it to mean. So I have mean minus x is the mean x. Minus x is the how much x is lower, no? And then I have to add this to mean x in order to have, no? So it is essentially 2 mean x minus x. I hope. And then let's check if, so if this is the same set y, 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 y. Okay, let's hope that this is working. Theta, okay. Theta, globals, tau, theta. Okay. I don't see anything. Maybe. Why they do not? It has a certain x, y. Yes. I have not. It is missing something. Set x core x or set xy x core x y. Otherwise, okay. Now, okay. So something is wrong. Some of them has went outside. So some of this condition is this is why. First of all, still not working. Which of these two? Let's try to comment all of this. So now they should move only in the x direction. So probably it's this one. If x is less than min x minus x let me put this here. Min x should be min x 31.5. So the problem is this. Yes, this is the problem. Min. Okay. Now I can uncomment this. Maybe we can. Okay, this behaves quite like a gas, no? And now, what do you want to put? We can put an absorber here at the end, Lucille?
Yep, I think an absorber would be nice.
Okay, so let me, to set up, I ask, so let min y is minus plus some 3. And so say ask patches with y core less than min y, set p color yellow with like this pi y core. Okay. So maybe we should not initialize. So let me move this here and x, say random float max x minus min x plus min x. This should be some random position between min and max x. And this y. Okay, so now we don't have things there, no? So now they are simply bumping also on this these things here. So maybe we can also do some other things. So let's suppose that they has also kinetic energy. k that we compute. For the moment, we don't have any collision. So here, say, set k m times vx square plus vy square divided by 2. So that we now can add the plot, say, histogram k of particles histogram k particle y max. Okay, this is redrawn only when I tick, so I have to put here tick. Why it is 50 here? Histogram key of particles. Okay, maybe I can increase the speed. I don't know why I don't see any histogram. Do they have all the same value? Oh. Let me see. Particle, inspect particles, K is 0.4. Well, I don't understand why I don't see the histogram. Maybe because I have to use bar. Okay, they have all the same speed, but strange. Okay, in any case, this is not really important. Even though I don't understand why they do have all the same. Okay. No, they don't have the same. Well, probably this histogram only works on integer or something like this. So maybe we can k times 100. No. Histogram never works. Okay. I don't see them. Yes, they don't evolve because they do not have any collision. Okay, so now let's put the collisions. Say streaming these boundary conditions. Okay. Now collision, and I now ask patches if count particles here greater or equal to 2, otherwise there is no collision. Let px sum m times vx of particles here. So this is the divided, say, let mm sum m of, this is the total mass, of particles here. X, this is divided by mm. This is the velocity of the center of mass in the x direction. This is the velocity in the y direction. Ask particles here. Now set Vx minus Px. Set Vy minus Py. Then I have to rotate of an angle theta. So I have to define a temporary variable because the rotation matrix gives the new x and the new y, but I cannot update the new x until I have updated the new y. So let the temp x, temp Vx, Vx times cosinus of theta plus Vy times sinus of theta. Set Vy temp Vx minus 1 times Vx times sinus of theta plus Vy times cosinus of theta. Set Vx temp x. And this should be the rotation of, then I have to set Vx plus Px, set Vy plus Py. And then should be all, but we have to define theta, I think. Set create, set theta is already defined. Okay. Let suppose this is working. Okay. Maybe with a small number of particles. Now something is not. Temp x, let temp Vx. Temp Vx. Maybe lower. Okay. Now you see that they collide, no? Sometimes. And now we should, I don't see this evolving much, but let's suppose that they start all with the same velocity. So instead of putting this, instead of this, I say set Vx cosinus of random 300, no, say let phi random 360. Let Vx cosinus of phi, set Vy sinus of phi. So now they all start with velocity, the same velocity, so the same energy. And okay. And in principle, if this, okay, let me, instead of doing this, I'll do this here. Not evolving at all. Why they do not thermalize? Because when you have more than when you have 3 particles, they should, according to the angle, thermalize. If count particles here greater than 2 mm sum of particles here. Okay, in any case, let me Let me investigate what happens to one of these. So, particle. So they all should be energy 0.5. No, energy is not changing, so probably it is a microcanonical. Even though when they have more than two particles, they should be able to I don't see. They're not really thermalizing. Okay. But it is not right. I cannot say yes. The problem is that I have to rotate them by a random angle between minus theta and theta, not by all the same angle. Otherwise, nothing happens. So let me say, let phi random float 2 times 2 times random float 1 minus 1 times theta phi worse than yes. This is the same for all particles. Okay. But they do not thermalize. They collide nicely, but okay, I have to think a bit to this. In any case, if now we can say, suppose that if one particle impact on this absorber with the kinetic energy greater than something, it is stopped, for instance, no? So let me come back to this because otherwise we have no variation in the initial energy. And so instead of this, instead of bouncing, let's suppose it is a simply, okay, with kinetic energy greater than something, you know? So if K is greater than, I don't know, 0.5, then something, if else. Otherwise, it simply bounces back. And what happens here? You may say, make another kind of particles, like stopped particles. So you can create stopped particles 1, set the shape circle set the color red, and then die. Could be. This is create a stopped particle. If else something wrong here. Create a store. It is not create. When a turtle creates another turtle, is a hatch. Because they are like animal, no? They hatch another animal. I don't know why. So you see that some particle stop there and from all greater than, say, a certain kinetic energy. Maybe we can put 0.2, and now you are selecting all particles with energy. Okay, I have still to understand why there is no thermalization of energy, but this can be a feature of this model. I don't know. What do you think, Lucille? This is something to start with.
Yep, it's very good. Thank you.
Okay, so let me save this, so you are free to go somewhere. Say multi-particle collision dynamics, and then I shall investigate thermalization in the Capral-Malevanez. So you see how we can, I don't say easy, but we can do some simulation more or less convincing.
Yep. We have to add maybe some more interactions, but yeah.
So now, the main point is the thermalization. I have to check how this happens in the multi-particle collision dynamics. Maybe on the Wikipedia page there is something, or in the original paper. In case I found something, I shall write to you. Do you sign it on the form?
Which form?
No, just to have your email address in order to send you something.
I mean, I think you might have it because I got some of your emails when you were trying to decide for the date.
Okay. So I think I have it. Okay.
Thank you.
So think if you want to try something, you can write to me in these days. I'm here, and we may meet together next Friday just to discuss or develop something together. Okay.
Okay.
Franco, yeah, thank you. Will you still be in Perpignan here tomorrow?
Yes, I'm here.
Okay, I will have to meet with you. It seems today is over because of the time. I have something similar to this because where I was having problem was how to adapt the coordinates to represent the change in vegetation status, change in land cover status. So I think this is a headway. Tomorrow I will try and make contact with you so we can discuss in person.
Okay, so send me an email describing a bit what you want to do. Okay. Because tomorrow I don't know where I will be, but at some time I will be available. But if you write down a bit the description, for me it's easier.
All right, thank you.
Okay, see you. Bye. Okay, now I can stop